In this video, we are going to look at the problems on the Chapter 11, Section 1 slides. Start here. If a single coin is tossed, find the probability that it will land on its top. Well, we can pretty much ignore the very rare case where the coin will land on its edge and stay. But in general, and the chances of a coin landing on its top or bottom are pretty much 50-50. So this is going to be 1/2. The probability of a coin landing on its top or heads is 1/2, approximately. It's very close to 1/2. For all intents and purposes, 1/2. Now we ask, if a plastic cup is tossed, find the probability that it will land on its top. This is one that is more difficult to understand. Based on the shape of the cup, it's more likely to land on its side. It's less likely to land on its bottom since it's more narrow. It would probably tip over and fall on its side. I did this experiment several times, and the authors of the book did the experiment as well. And when the authors did the experiment, they found that out of 50 tosses, the cup landed on its top 5 times out of 50. Which is 1/10. And that is could just be the way that they were tossing it, but it seems about right. Kathy wants to have exactly 2 daughters, assuming that boy and girl babies are equally likely. Find her probability of success for the following cases. If she has a total of 2 children, well, how many ways are there of having 2 children? We could have 2 boys, a girl and a boy and a girl, and this counts for order, or 2 girls. The chances of having exactly 2 children, 2 girls, and out of 2 children is 1 in 4. If she has 3 children, there are now 8 possibilities. You can have 3 boys, 2 boys and a girl, a boy, a girl, and then another boy, a boy and 2 girls, a girl and 2 boys, a girl, a boy, and another girl, 2 girls, and then a boy, or 3 girls. There are here 1, 2, 3 cases where there are exactly 2 girls. That's 3 out of 8. The probability of 2 girls in 3 births is 3/8. Sure that's showing up for you guys. Good. Okay. If she has a total of 14 children, now we have 16 possibilities. B, 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 G, B, B, G, B, 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 G, G. And I'll circle that one because there are 2 girls in it. B, G, B, 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 G, B, G. Circle that. B, G, G, B, B, G, G, G. G, B, 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 G, B, B, G, B, G, B, G, B, G, B, G, G. G, G, B, B, G, G, B, G, 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 B, G, 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 G. So we have found 6 out of 16. Which is the same as 3/8. Sorry, my clipboard moves around a bit when I'm working, so hopefully you see the important stuff. Find the probability of being dealt each of the following hands. Use a calculator to obtain answers to 8 decimal places. The probability of being dealt a full house, that is the probability of being dealt probability of being dealt 3 of one card and 2 of another. Okay, well, there are 3,744 different full houses and 2,598,960 different hands of cards. Had to grab those numbers from the book, and then I dropped the book, which is fun. Get it back when we need it. So I break out my calculator and I do my division. 3,744 divided by 2,598,960 gives us 0.001440506. Wait, 0.058. There we go. That's it to 8 decimal places. Not the greatest probability. For a royal flush, there are only 4 ways to get a royal flush. So the probability here is 4 over 2,598,960. Which gives us a probability to 8 decimal places of 0.0000154. According to the U.S. Census figures, on July 14th, 2018, there were an estimated 162.4 million males and 166.9 million females living in the USA. If a person were randomly selected from the population in that year, what is the probability that the person would be male? Well, to do this, the first thing we want to do is we want to add these two numbers. 162.4 plus 166.9 gives us that gives us 329.3 million people in the US. So to find the probability that a male is selected, we divide 162.4 over 329.3. Which gives us a probability to 8 decimal places. We don't need that many, but close enough, of 0.4931672. We could easily round that to about 0.49 and be happy with that. Fair coin was tossed 35 times, producing the following sequences of outcomes. And we've got 7 sets of 5 outcomes here. We want to calculate the ratio of heads to total tosses after the first toss, the second toss, and so on through the 35 tosses, and plot those ratios on a graph. So for the first toss, it's a tail. So that's 0 to 1. That's our ratio. It's 0. Second toss is another tail, so that's 0 over 2, which is still 0. Third toss is a head. That's 1/3. Fourth toss is a head, so that's 2/4 or 1/2. Fifth toss is a head, so that's 3/5. Then we've got 3 tails in a row, so that's going to be 3/6 or 1/2. 3/7, 3/8. 2 more heads, 4/9, 4/10, which is the same as 2/5. Another head, that gives us 5/11. That should have been 5/10. 5/10, not 4/10, which is 1/2 again. Yeah. Okay. Sorry about that. Okay, so now we've got 6/11. 6/12 is 1/2. 7/13. 7/14 is 1/2. 7/15. 8/16, which is 1/2. 9/17. But then we get a tail, and we're down to 9/18, which is 1/2. And a head gives us 10/19, and another head is 11/20. Another tail brings us to 11/21. Another tail, 11/22, which is 1/2. Another tail, 11/23. Another head, 12/24 is 1/2. Another head, 13/25. Another tail, 13/26, which is 1/2. Another head, 14/27. Another tail, 14/28, 1/2. Another tail, 14/29. Another tail, 14/30, which is 7/15. Another head, 15/31. Another head, 15/32, which is 16/32, which is 1/2. Another tail, 16/33, another head, 17/34 is 1/2. And finally, one more head brings us to 18/35. Now, rather than trying to sketch a graph of this, I'm just going to show you the one in the book, which is right here. You can see how this starts at the bottom. There are 2 zeros, and it goes up to a third, then a half, and then it wiggles around the line representing 1/2. And that's more or less what we would expect this to happen here. Referring to the table below, determine the probability that a third generation will exhibit each flower color. Base the probabilities on the sample space of equally likely outcomes. So here we are asked, we've got, sorry. Generation will exhibit each flower color. Okay, so these are our equally likely outcomes. We've got our first generation each had one dominant red trait, one dominant R and one recessive lowercase r. If we get a, if we get any big R, then the flowers will be red. If we get 2 little r's, the flowers are white. So we need to figure out what we're likely to get from our third generation. And that comes down to a number of things. First off, if one of the parents has two big R's, all of the kids will be red. So that's, if we have 2 big RRs or 2 big RR, 1 big R, 1 big R, 1 little r, big R, 1 big RR, or 1 big RR, 1 little r, we're going to wind up with red flowers. So we can right off the bat say we've got 16, which always result. That's just a start, though. We've got to deal with the other possibilities here. Now, if we take a big red, little red, and match it with a little red, big red, or with another big red, little red, we've got, then we are going to get basically the same pattern. So in 2 cases, we will have 3 red sets of red flowers. In fact, this is 4 cases. Yeah. In 4 cases, we will have 3 sets of red and 1 of white. So that's 12 always red and 4 always white. The only remaining case is when we have 2 whites alone. Actually, if we match either of these with a white with two recessives, or if we have those all together. So if we match these with these, that's another 4 always white. The last thing to consider is if we have either of these with 2 always white, and we'll set that up. Okay, so a big R with a little r is RR, big R, RR, little r, In this case, or if we do it with the other one, we will have we will have 2 red and 2 white. So we can make that 4 red, 4 white. Sounds about right to me, I think. So yeah, we match these two with any of those that account, including itself, we've got pure red. If we match either of these with each other, that should actually be 32 because it's possible that this is the second parent instead of the first. If we match these with each other and vice versa, we'll get 3/4 of the time we get red and 1/4 of the time we get white. If we match either of these with the white, we get, so it's going to be, yeah, this should be 64, I think. Let's add it up. Sorry, I'm all over the place here. I apologize. 32 plus 12, 12 plus 4 plus 4 plus 4 plus 4. I think we're missing 2. I'm not sure what we're missing. Let's do this. These are the possible combinations we can have. Now, obviously, we've already accounted for both of the parents being all dominant traits. So now we'll consider if we've got the first parent having one recessive and the second having both dominant, we've got 4 red flowers. If we've got same here, that's 4 red flowers. And if we've got 2 recessive for the first parent and 2 dominant for the second, that's all red again. Now we move on to the somewhat more complicated cases. If we've got 2 flowers like this, we will get 3 red and 1 white. The same is going to happen if we have something like that. Or if we have this. Or if we have this. If we have something like that, then we have 2 red and 2 white. Same happens if we've got, or if we reverse these. So that gives us 8 red and 8 white. The only remaining combination is for us to have all recessive, and that's going to give us 4 white. Okay, so here are all of the possibilities. We've got 16, 28, 28 plus 12 is 40, 48 red flower possibilities, and 4, 8, 16 white flower possibilities. This is good because that's 64 and that's the number we want. The probability of a red flower is 48 out of 64, which is 3/4. The probability of a white flower is 16 out of 64, which is 1/4. Sorry that took so long. Last problem for this video, I think. No, we might have a couple more. Teresa has been promised one of 6 jobs, 3 of which would be intern positions at the state capitol. If she has equal chances for all 6 jobs, find the odds in favor of her getting one of the intern positions. Well, if she has equal chances for all 6 jobs, then it's basically 50-50 that she'll get an intern position. She has a 50% chance of getting an intern position. So that's 3 to 3, which we simplify to 1 to 1 odds. Bob has purchased 12 tickets for an office raffle in which the winner will receive an iPad. If 104 tickets were sold altogether and each has an equal chance of winning, what are Bob's odds against winning the iPad? Okay, so we know that there are 104 tickets bought, and he bought 12 of those. That means that there are 92 tickets that were purchased that he didn't buy. So that's 92 to 12, which simplifies to 13. No, not 13. I'm sorry. 92 divided by 4 is 23 to 3. Those are his odds against winning the iPad. And this is the second to last problem. There is a 30% chance of rain tomorrow. What are the odds in favor of rain? What are the odds against rain? Okay, the odds in favor of rain, there's a 30% chance of rain. That means that there is a 70% chance it won't rain. So that's 30 to 70 or 3 to 7 odds in favor of rain. And we just reverse that and get 7 to 3 odds against. Finally, in a certain sweepstakes, your odds of winning are 1 in 99,999. What is the probability that you will win? The probability you will win is 1 in 100,000. Your odds of winning are 1 in 99,999, means that that's 1 over 1 plus 9,999, which is 1 over 100,000, or 0.00001. That's it for this video. If you have any questions, please get in touch.